So hello and welcome everybody. It's a great honor to be presenting to you the results of my thesis, AI-driven multimodal joint analysis and prediction today. And this is a work as a cooperation between the Robotics Institute of Munich and the Department for Orthopedics and Sports Orthopedics. So let's dive right in. Today we're going to first be looking at the introduction. How do we come to the research that we conducted in the first place? What are the challenges? Then I will present to you the main contributions. And finally, I will conclude with the limitations and the outlook. So, general, how did we come to the subject of AI-driven multimodal joint analysis and prediction? So in the general orthopedic workflows or the orthopedic clinic, we have some challenges, which are currently a high shortage of manpower. So we have a sharp increase in elderly population coupled to a shrinking workforce. Further, we have a rising expected cost, which is about to be about 40% only by the year of 2030. And in order to somehow counterbalance these effects, there is the potential role of technology here. So what can AI and robotics do to be key solutions for enhancing orthopedic care and also the efficiency? What can be done in a way? So what could be done with AI and robotics? One thing would be to improve the diagnostic accuracy, the surgical precision for the future, and of course, finally, also the patient outcomes. So building on that, let's take a closer look at the current clinical workflow. So we have the preoperative patient in the first place. Then this one will extend to the preoperative analysis, followed by then the intraoperative patient, and finally, after the operation, the postoperative patient. What can now be done? Well, in order to somehow get a better understanding of what is happening here, we need objective data. And how can we obtain that objective data? Via the means of digitalization in the first place. So that is one challenge. The other challenges are then on how to use that available data. So going into the data analysis scheme. We can improve joint analysis, so get a better understanding of the current joints. If we have that joint analysis available, we can then predict the outcome for the future, and finally provide patient-specific treatment. So building on this general workflow, we came up with the 4 central research questions that I will be presenting to you right now that were defining the background of my thesis. So first of all, let's take a look at the preoperative phase and the postoperative phase. So the phase out of the clinic, and what can be done here? We can provide wearable devices. And the question is, how can wearable robotics enhance the orthopedic workflows? Also by providing data for joint disease prevention and also finally then for rehabilitation. Second, if we enter the clinic, then we enter the preoperative analysis stage. And again, here the question, how can AI support diagnostics and surgical planning using orthopedic imaging, for example? Then if we need the operation and we are in the operational stage, then it would be very beneficial to have a better understanding of the joint itself. So how can robotics advance joint analysis in orthopedics? Here we're going to be focusing on the knee and hand joints only. So for mainly using robotic test benches. And finally, if we have those robotic test benches available, how can we build digital twins based on the data that we collected? So that is those are the 4 central research questions that we were looking upon. And now let's take a look at the main contributions. So this is the overview of all the main contributions that were developed during the intercourse of my thesis. So again, you can see the clinical workflow here on the top, and then based on those, the 4 central research questions and the respective projects that were conducted. So let's now take a closer look at the first part. So we're going to be looking at pre- and post-operative data, and then using the wearable devices as the tools we're going to be taking a closer look at. First of all, let's take a look at a device that is just passive. What does that mean? That device is just there for pure measurement. It doesn't really interact with the patient in a way. So one thing we developed here is an IMU-based system, internal measurement, unit system that measures the orientation in space, and it can provide us with sufficient gait analysis data. Why do we need it? Well, in the clinical current stage, you want to know the gait of a person, but it is very time consuming and expensive because you need a laboratory environment, you need a video-based system to measure that, and we came up with a simple method of providing an alternative which has comparable accuracy. So that is a passive system that we developed. Let's take a look at an active system. So now we want to get more active during therapy. We also want to be part of the therapy. Therefore, we took a different look at another problem that occurs in the clinic in orthopedics, and that is CRPS, complex regional pain syndrome. This syndrome occurs after heavy disease of the patient, and this leads to a high pain induced in motion. So if the patient has, for example, his hand and he's trying to move for example, the finger, it is coupled to a high pain. That means the patient doesn't want to use really the respective finger, which leads to a negative cycle, meaning that in the end, it doesn't really look good for the patient. As the negative cycle increases, the stiffness increases, and we want to break that cycle using an exoskeleton device in that case. So we developed the following device. Let's take a closer look at what we came up with here to break that negative cycle, to provide motion and also measurements at the same time. So we can see here we're measuring 3 different position sensors, one single force sensor, and a linear motor to actually get active during therapy. And with that, we have a very nice basis that can be extended for future use cases. So what is so special about the kinematic structure of that respective exoskeleton? Let's take a look at the current kinematic structure. So providing a single external measurement, and we can solve for all the different rod forces clearly, and then giving that, we can only calculate the external forces that are actually induced here, mentioned in red, that are actually occurring on the actual finger. That means it allows us not only to solve with the respective sensors for the trajectories, but also for the loads in the finger joints, as we can see here. So that is very nice. It allows us to not only interact with the patient, but also to measure all the requirements. So now let's bring that to the clinic. That was the main challenge that we extended this exoskeleton upon, and we wanted to really use that exoskeleton device in rehabilitation. So what was missing? Mainly, of course, it's only for a single finger, but another limitation is that it's not really interactive in a way. So we developed a mobile application which builds on those tasks, and we also developed some games to make the therapy a bit more fun, so to gamify the process. On the left, you can see a game that is motivated by motion. So here, the patient is motivated to move the finger and is being rewarded by collecting something like these balls. And on the right, the force is rewarded. So you can apply a force and then accelerate the orange ball you can see here on the screen. And by doing that, you can avoid the rectangles. So different kinds of rewards and different kinds of therapy ideas. So this doesn't only allow to really gamify the therapy process, to be using the finger and getting rewards, but also to measure the patient's progress during rehabilitation. We can see that here for a single patient that is being compared after 4 weeks of therapy. So because the exoskeleton allows to be used in a very reproductive manner, so you can really measure the same movement after a long period of time, you can track the differences. So here you can see almost no differences in the angle trajectories, but high difference in the torque trajectories, meaning that the stiffness of the patient decreased over time and giving an objectification to the actual very subjective clinical scores that exist right now for CRPS. So how can this be extended? We just presented the current results at the last IROS. We now extended the whole exoskeleton not to be used by a single finger, but for all long fingers. And then for the future, we are thinking about maybe extending it also for the thumb. So that is one thing for the out of clinical stage. So we're not really needing the the operative phase right now. So let's dive in what is required or what can be done using AI and robotics in the preoperative analysis stage. So we have images, we are in the clinic, and we want to optimize the processes in there. So because this analysis is mainly focused on images, we need some kind of way of dealing efficiently with images. And one thing we really need is, if we want to train then AI algorithms to support us, we need the knowledge of the physician in the first place. And because this process is very tedious, they came up with a simple application that allows you to actually use the annotation process in a more efficient manner by providing this application. So it's very easy for the physician to actually annotate and segment images. Building on that, we can then actually develop tools that are really beneficial for the therapy or for the process during the clinical workflow. So the first thing we looked upon is actually providing tools that are really important for the clinic. And that is one thing, to detect severe diseases, such as primary bone tumors on radiographs. So back then when we started in 2020, there were no automatic tools for detecting this. We were one of the first to develop the solution building on that. And we only had a very limited training data set, only 650 images. And that meant we had to be very efficient about the way we were using each of those images and gaining as much knowledge from a single image as possible. How were we able to do that? Well, we used some kind of multitask learning. So we didn't just provide the algorithm with a single task to do, but with multiple tasks. In this case, you can see it here. So the network doesn't only have to do a single classification prediction, but this is also extended by a bounding box placement, by a segmentation, and all of these different tasks work more or less as synergy for one single backbone. So this mask RCNN that we were using has all the different tasks applied to it at the same time, and so the single backbone learns from all of the different tasks. How good does it perform? We can see it here. It already performed quite decent on the classification here, but to give it some more perspective or relative perspective, we now take a close look at the accuracy. So you can see here the accuracy of that very first bone tumor detection algorithm was already quite good in detecting the right class of the bone tumors in 81% of cases. Comparing that, for example, to the clinical practice, how good is an assistant physician after 2 years of experiences is only by 71%, and this is only being beaten by the actual fellowship trained radiologist. So the real expert exceeds it by 3%. Okay, so very nice study to showing what is possible using AI algorithms and what is then possible for the future, as we were only using a very small data set here. A different kind of study we performed also is more aligned to a classical clinical workflow for orthopedics. So hopefully you don't have a bone tumor. Now that is excluded by the first network. Let's now take a look at something like lower extremity alignment analysis. That means we want to train a network that can actually calculate our lower leg angles. So what is required here? Again, we had a reduced data set because it was a very tedious process of annotating all those images. And so we had to again come up with a very sophisticated solution for the problem. You can see it here. And we have a very large image here as the basis for our network. So we need at the first stage to localize parts of that image. So to know where is, for example, the hip, where is the talus, etc. And by performing that localization step, we can maintain the maximum accuracy possible. Then we can perform expert network analysis on that cropped image, and then finally project the results back on our overall image and calculate the respective leg angles based on this. So sometimes there are some kind of misconceptions with the key point accuracies, which are very important for that network. So we also extended this by using local key point filters to further optimize this accuracy. So how good did this network perform? Well, overall, the results were quite astonishing. An overview here on the right. but just to summarize it, the accuracy was below 1 degree compared to the orthopedic surgeons, and the interclass correlation was over 90%. And the main difference is it just saves a lot of time. So using the deep learning model is just requiring 12 seconds compared to an experienced orthopedic surgeon who takes about 90 seconds if he's really good at this process. Okay, so now the current state of the art that we can provide right here. So this is the current state of that network being used in the use case. So it allows for just using everything on a web application. It is not limited to just realignment analysis, but it can also perform osteotomy planning. You can see that right here. The web application that I developed is able to really annotate the images as desired, building on the initial network detections, and then also perform the actual realignment surgery. So if you want to have altered leg angle, you get the proposed surgery to you presented right there, and you can also alter it and calculate it. We compared that in a clinical study already and are preparing the publication as of we're speaking right now, and we saw some very good results in automatically calculating all those required accuracy, correction angles, and correction lengths. So really nice final thing to be supporting the preoperative analysis stage right here. So how can we now extend on that stage and not only look at imaging data? So right now we were only in the clinical phase looking at imaging data, and now our thesis is called multimodal joint analysis. So let's extend this to a more sophisticated stage also. So if we are entering the intraoperative phase, where we at the first time get available different kinds of data, for example, force torque data, etc., we now want to provide tools that can allow us to measure those new data types, and also to be using them for a more sophisticated joint analysis that is not only limited to imaging data. So let's dive right in. The first thing I had to develop, so I just want to mention it quickly, is to use those robotic test benches in a sophisticated manner. So what we are using here is building control algorithms that were able to actually dealing with the unknown specimens in a proper way. So we were mainly doing research on specimens here. And you can see an extension that I developed right here, which was very important for us as we were often being confronted with different kind of tasks. So there are force tasks, there are position tasks, and those kind of interfere with each other. So it's very difficult to separate them from another, and that makes the algorithm the control algorithm much more stable. So I came up with a solution that uses automatic supervisory control that allows us then to really decouple the position task, you can see it maybe right here, from the force task. Or as we then designed it, we were putting the emphasis on the force task, so the position task was being neglected and the force task was prioritized. And we had some nice results in showing the differences of using the different kinds of prioritization, and we're able to actually extend on a classical hybrid parallel control algorithm, as it was a bit more robust for really coupled tasks. So the second thing I'd like to present to you then, building on having a sophisticated control architecture available, is then really using some of those test benches for gathering valuable information during the clinical process. So one thing we were looking upon was then comparing different kinds of implant rotation effects during a total knee arthroplasty, for example. So during knee arthroplasty, you replace the femur and the tibia with some kind of implants, and the orientation of the alignment, of course, matters greatly. So you can see here on the right, there is a femur shield being rotated by +5 degree, neutral, or -5 degree position, and we were able to have a really sophisticated test set up using the robotic test bench presented. And what we were then able to do is just not compare the different kinds of rotation effects, but also compare it to the native knee joint in the first place. So that allows us to really get some more sophisticated data and comparing the behavior of those different implant rotation effects to the native knee joint. And in this case, we find that the high precision was achieved for the +5 degree rotated femur shield in that case. So a robotic test bench allows for very sophisticated data. Of course, on the same time, we always collect the data to get some more sophisticated data for the future. Now we have that built for the knee joint. Let's take a look of how we can get a better understanding for something more complex in a way, such as the human hand, as it has much more degrees of freedom available. As we saw, a really sophisticated test bench to really track the whole system in a closed loop scenario. So to know if I actuate my hand by external forces, what will be the resulting motions of that respective hand. A test bench that is able to do that is not being implemented yet. And that is very exciting and a true challenge for us to come up with a solution for that scenario. So what we developed then is a robotic test bench that is consisting of 8 individual electric motors that are being controlled on 20 kilohertz internally and 550 hertz out externally to be actually force controlled in the end. We extended the whole system by an optical measurement system and also a video capture to evaluate what was actually going on. So the test bench you can see right here. It is really sophisticated, as you can see. So there are the electric motors on the top. Then each electric motor is connected via a tendon and being deflected right here where we have the force measurements, and then being connected to the actual tendon of the hand, the specimen hand. So the hand itself has some optical trackers right here down below to actually also track the motion exactly. Further, we have an external force torque sensor that we can further apply if we need to actually also measure the resulting pincer grip forces. So that was one of the challenges we were looking upon. Can we then actually also use that test bench to apply something complex such as the pincer grip? And we can see that right here. So the results were really nice. This is the live result of the test bench. So the tendons here in the back are being actuated. That leads to a tension in the respective hand tendon, and then we can see the resulting motion here and the capture of the external gripping force for the pincer grip. So that was one of the nice results, that was actually being able to do that. We have now the closed loop, and now we want to also formalize a model based on this, so we can really also recalculate the actual finger trajectories based on this. So we can look at the individual angular joints over time and also the activating external forces of the respective tendons, respective muscles. How does that look on reconstruction of the 3D scene? So you can see that here on the right, we were also able to recalculate every motion that was going on and then build the model based on this. And that is a good last point that I want to emphasize here. So giving these test benches, we were now able to collect valuable data in the first place. That was what one of the main tasks is all about for more sophisticated joint analysis. But how can we then use the data in the most efficient manner? And one thing we really want to build is to be able to formalize digital twins based on the data we have available, because then we can really simulate and predict future behavior. So in order to formalize these digital twins, we need some kind of optimization that actually does fit our data that we collected to the respective models we want to formalize. And we have two challenges here, mainly to bring it down or to cut it short a bit, and those are the kinematic optimization and the dynamic optimizations. So let's take a look at the kinematic optimization. So it is a bit different to classical robotics in a way, because in classical robotics, you already know that. You know the exact kinematic structure of your model in the first place because you formulated it that way. So you have your CAD files, etc., and you know the kinematic structure. In specimen analysis and biomechanics, it's a bit more difficult because each specimen is unique and the joints will not be in the same spot all the times. So you need some kind of automatic toolbox to actually determine the position of those joint axes. And what we came up with is a structure that is more closely related to an autoencoder from informatics. So it just uses the available measurement positions, then creates a compression, which are the angular representations in the middle, and finally does a reconstruction of the measurement positions. This creates an optimization loop that we can actually exploit and optimize upon if we formalize the right decoder and encoder architectures. So that means an encoder in this term would be inverse kinematics, and a decoder would be forward kinematics. Can we just use any kind of decoder or encoder? Of course we cannot. We have to really pay attention to the actual model design. So our decoder, which is our forward kinematics model, has to exactly represent the structure of the specimen in general. So that means it has to know how many rigid bodies and joints are included into the process. If that is available, then we can optimize upon this and formalize the whole thing autonomously. So during optimization, this is just a schematic reproduction of the results that we obtained, and we can then see, given a general position of the axis, it allows us to then really detect the actual axis of rotation for the individual specimen. So here demonstrated for the hand joint and the knee joint. So given that, this optimization then gives us a good starting point, as we have the forward kinematics solved in an accurate manner. So building on that, and that is one of the main challenges that my dissertation unfortunately will not be able to be solving in a complete manner, and just give some more ideas on how this can be solved, is to use some kind of further optimization on those kinematic optimized models. And one thing to do is to use reinforcement learning for that, to create some kind of adaptive models, and we have some kind of parameters that we want to optimize upon. And a very simple manner is to simply compare the behavior of the simulation with the behavior of the measurement, and formalize the difference as some kind of loss that we want to generally be optimizing upon. We cannot differentiate back through the whole system because the dynamics in general are not always differentiable itself. So we use a surrogate objective, which is just the difference between those two, and try to optimize using reinforcement learning. We saw some preliminary nice results using that, especially for soft ectocritic and PPO approaches. And we could see that those approaches were also able to then identify correctly very simple initial models that we were testing upon. More complex models, the optimizer also tends to sometimes fail because there is not enough modeling and not enough data available for these optimizers. So with that, I would like to conclude the current state of my thesis, and also first of all give some more emphasis on the current limitations of the results I presented to you. So first of all, this is not a complete framework that is just working, everything is working together. Some of these projects are of course modularly isolated. For example, the realignment surgery planning does not really interfere with the exoskeleton system, so it is modular isolated. And we also focused on knee and hand joints only here. And also a big limitation is that, of course, ex vivo data does not always 100% predict actual patient's behavior for the future. Then, as the diagnostic toolbox that I presented to you is already being used for research purposes, I would really like to emphasize further that this tool doesn't have any kind of certification for being used in the clinic as of today. So please be aware of that and use it with caution. And finally, the prediction part, so we really are already able to predict what will happen, is only for the surgery planning currently completed. So let's take a look at what we achieved in an overall manner. You can see all the projects I really went over the last 15 minutes. So you can see there are a lot of papers already being published as of today, marked in green, and also we were able to fortunately obtain some research prizes. Then how will it look for the future? What are projects that I will be still very interested in further exploring? That will be, for one thing, we now have the overall hand exoskeleton to really bring that to a rehabilitation study then for the whole hand. Further, we are currently working on extending the preoperative planning algorithm to be used on also for total knee arthroplasties. Then for the coming summer, I was planning to actually do some research on the hand that will then also be using in model predictive control as a background, and where we have some preliminary nice results. And then further, we wanted to further optimize the automatic knee identification by also using a cooperation of the robot, and also by improving the dynamic optimization part, which will of course still be very challenging. So with that, I would also like to put some more emphasis on the rewards that we received. So mainly focusing here, was really nice to receive the Digitalization Award at last year's DKU. And with that, I would like to thank you all. Thank everybody who participated and helped me during the years of my PhD thesis, especially my supervisors, of course also my students, and finally my important collaborators. So thank you very much, and I hope you take something from this small presentation of my thesis. Thank you.